welcome to the trigonometry series. So what's trigonometry? Well, if you break down the word, it essentially means the study of triangles. And yes, we are going to get really awesome at everything triangles. But a lot of the power of trig also comes into play when you're talking about things that on the surface seem to have nothing to do with triangles. But before we could begin to unpack any of that stuff, let's start with the basic stuff because there's enough fun to be had there. Let's start with triangles. And the right place to start, no pun intended, is the right triangle. So why should we start with the right triangle as opposed to the acute or obtuse triangle? Well, one reason is that we know exactly what one of the angles is. It's exactly equal to 90 degrees. And otherwise that would be a variable, so the fact that it's a specific number makes it easier to deal with. So that's one reason, but another reason is that acute triangles and obtuse triangles are actually made of right triangles. And if you draw an altitude in the triangles, you will see that. So if I drop an altitude in an acute triangle, then I can see that it's really just two right triangles joined together at a side. The same is true of an obtuse triangle. If I draw this altitude right here, I can see again that I could think about an obtuse triangle as two right triangles. So if I get really good at right triangles, then I really have all the ingredients I need to be good at acute triangles and obtuse triangles. So really, a really good way into studying all triangles is just to focus your attention on the right triangle. The power goes beyond just triangles, right? So if you think about any polygon at all, you can cut it up into triangles, right? So if I just drop diagonals in this case, so this hexagon here, but you could do this with any polygon, can be cut up into triangles. So this hexagon can be cut into, looks like 4 triangles. And each of those triangles can be cut further into right triangles. So if you think of polygons as molecules, the atoms that make them up are the right triangles. So the point is that right triangles are really worth studying because they tell you a lot about things that are not just right triangles. And again, what is this other thing? So other is stuff that's not even related to right triangles, apparently. So for example, if you're thinking about the motion of a particle that's going around and around in a circle, or you think about an object that's on a spring that's oscillating back and forth, and you want to describe the motion of these things, then it turns out that a deep understanding of triangles and trigonometry is not only useful, it's absolutely fundamental. And so all this to say that right triangles are definitely worth studying because they tell you about things that are a lot more than right triangles. So with that being said, let me tell you the foundation of all of trigonometry. Okay, and this is what it is basically. If I tell you one of the angles in a right triangle, so let's say I tell you this angle is, I don't know, 14 degrees, then if I specify this angle here, I've actually specified a lot more than just that angle. For example, one thing I've specified by specifying this angle is this other remaining angle. So the first fact is that the last angle is fixed. That's if I, say that one of the angles is a specific value, the last angle has to be fixed. What that means is I can't just make it whatever I want it to be. I can't make it 70 degrees just because I want it to be 70 degrees. It's a specific number and it has to be that number. The second fact, and this is really the heart of trigonometry, the fact that makes trig go, is it's not just the last angle that's fixed, it's also the ratio between any two sides of this triangle is fixed. So the shape of the triangle is sort of locked into place. So the ratio of this side to this side, for example, is some specific fixed number. The ratio of this side to this side, for example, is some other specific fixed number. And again, I don't know what those numbers are right now, but I can't just pretend like they're whatever I want them to be. I can't just say, oh, this side is 10 and this side is 5. Because that would imply the ratio between this side and this side is 2, and how am I supposed to know that that is the prescribed ratio, right? So I don't know that. So I can't just make sides whatever I want them to be like that. Like I can make that 10, but that would set into stone what that side has to be because the ratio is set into stone. And so to write that down, so the point 2 is the ratio between any two sides is fixed. So these facts are the foundation of trigonometry, okay? We're going to use these facts heavily, so it is worth spending some time to justify them. Okay? So why is the last angle fixed? Well, if you recall from geometry, one of the theorems there is that all of the angles in a triangle add up to 180 degrees. And so if that's 90 and that's 14, then if everything adds up to 180, that has to be 76 degrees, right? So it's easy to work that out. So the last angle in this case is 76 degrees. So it's easy to convince yourself that the angle is fixed because you can evaluate exactly what it is. It's equal 76 degrees, right? The second fact is a little bit deeper and more mysterious. It's not obvious at all why it's the case that the ratio between this side to this side, for example, is fixed. What is that ratio, by the way, you might be wondering? It's about 1 to 4. So if I make this 10, then this side I can't make it 5 because the ratio is fixed. It's 1 to 4, so this side would have to be 40. But how do I know that the ratio has to be something specific at all? Again, we need to reach into our bag of geometry tricks, right? So if you recall from geometry, so here's another right triangle with a 14-degree angle in it. One of the facts that we learn in geometry is angle-angle similarity, which is that if you have two triangles and two of the angles are the same, so 14, 14, 90, 90, then the triangles are similar, meaning that they're a zoomed in or zoomed out version of each other. And if you're a zoomed in or zoomed out version of each other, you have the same shape, you just have a different size. And so the relative ratio of any two of your sides is going to be the same, like regardless of which triangle you are. So this triangle, if this is 1 long, this would have to be 4 long. They would have to have the same ratio because they are similar triangles. And so the point is, any right triangle with a 14-degree angle in it is a part of this infinite family of right triangles with a 14-degree angle in it, all of which are similar to each other, so all of which have the same ratio. And so that fact that they're all similar and have the same ratio makes it a very fixed, specific ratio. So that is the long-winded geometric justification as to why exactly it's the case that when we know this angle, then we know for sure that all the ratios between any two sides of the triangle is fixed. Right? So that's the justification. But from now on, we're going to work with it as if it's an assumption going forward. Okay, so, but let's before I erase this completely, let's think about this ratio of 1 to 4. How would I express this thought? Like, how do I express this idea that I have here? It would take a lot of words. I would have to say, in a right triangle with a 14-degree angle, the ratio of the side opposite that angle to the side adjacent to that angle is 1 to 4. That's a very long-winded idea to express a relatively simple mathematical thought. So trigonometry, a lot of it is going to be building a language to make talking about ideas like this a lot easier. And in order to do that, we need a system. So in this picture, everything is a variable instead of a specific number like 14, because that way we can talk about all right triangles simultaneously. So let's call this angle theta, and let's call the sides A, B, and the hypotenuse C. And one important thing to keep in mind is this important fact that theta is an acute angle. It's always going to be between 0 and 90 degrees. It can't be below 0 because it's an angle that lives inside a right triangle, and it can't be 90 or more because then there would be too much angle for the triangle to fit inside it. There'd be more than 180 degrees. So that's just something that we should always be keeping in mind when we do trig. But with that being said, once you fix theta to be something specific, we talked about how the ratio between any two sides is technically fixed. And so how do we talk about those ratios in a concise way? How would we talk about the ratio of A to C, for example? Well, we would have to start naming things. And so the name for that particular ratio is called the sine of theta. So mathematically, you can write sin of theta. And if you want, you can put parentheses around the theta. It means the same thing. And the sine of theta represents the opposite side, or the ratio of the opposite side to theta to the hypotenuse, which in this example would be A over C. That's one. The cosine of theta is the ratio of the adjacent side to the hypotenuse. So that's designated COS of theta, or cos of theta, and that is adjacent over hypotenuse, which we could write as B over C. And finally, we have the tangent of theta, which is, you could write as TAN, or tan of theta, and that is the opposite sides to the ratio of the opposite side to the adjacent side. So that is opposite over adjacent, and that would equal, in this picture, A over B. Okay, so this is our new language system, if you will. So that previous thought that we had about the 14-degree angle and the ratio of the opposite and the adjacent, how would we say that with this new language? Well, that ratio was this side to this side, opposite, adjacent, so that was the tan. So what we really were trying to say in a convoluted way is this: tan of 14 degrees is a quarter. That's what we were trying to say. And by the way, you might get, early on, you might be confused as to which ratio means which thing. Like you might get sine confused with adjacent over hypotenuse, or you're getting confused with cosine. How do you keep them straight in your mind, you might wonder? Well, one helpful mnemonic that most of the world uses is SOH CAH TOA. SOH CAH TOA. If you could remember that, then you remember what the ratios are, because sine is opposite over hypotenuse, SOH, cosine adjacent hypotenuse, tangent opposite adjacent. So that's one helpful way of keeping them straight in your head, just a helpful tip. And at this point, you might have a very valid question, which is, who cares that the tan of 14 degrees is 1 over 4? When would that ever be useful to anyone ever? And it's a hard question, but and it's a fair question, but let me give you just one example of when it might be useful to someone ever, just to sort of satisfy that curiosity. Okay, so let's just say that you're on a boat. Okay, just pretend that you're on a boat. And let's say that you are some distance from shore. And that's the fundamental distance that you're interested in thinking about, because you're on the boat trying to get to shore. So you might be curious, well, how far away from shore am I? And let's say the only piece of information you have is that you know that there's this lighthouse that's on the shore. So that is a fine drawing of a lighthouse. And let's say that you know that that lighthouse is 1,000 feet tall. And it's standing straight up, so presumably it makes a right angle there. And you have some navigational equipment on the boat. Let's say that you can tell the angle from your boat to the top of that lighthouse is 14 degrees. Then, if you know that the tan of 14 degrees is 1 over 4, you can deduce how far you are from shore, right? How far are you? Well, if it's 1 to 4 ratio, you would have to be 4,000 feet from shore, right? So that's an example of why trig could be useful. And it's a fair response to say, what if it wasn't 14 degrees, right? Like what if it was like literally anything else? And obviously, if you get good at trig, you could handle the situation no matter what the angle is. And again, you might be wondering, well, how would I even know that tan of 14 degrees is 1 over 4? How did you figure that out, for example? Well, to tell you the truth, the way that I figured it out was I put it into a calculator. And that's okay. You'll have to do that a lot of the time. A calculator will tell you what any of these ratios are for any angle. But you don't want to have to rely on a calculator to do trig. There are a lot of theta values, angles, where you should know what the sine, cosine, and tan are, because it's rather intuitive. And so to start that sort of numerical foundation building, so we don't always find these ratios scarier than they need to be, let's build a basic table of trig values. Geometry so far has been indispensable to our reasoning, and it's going to continue to be for this particular table. So we're going to need two special right triangles from geometry. The first is the 45, 45, 90 triangle, which looks something like this. And if that were 45 and that were 45, then the fact that we need from geometry is that when we have two angles that are congruent in a triangle, the sides opposite those two sides must also be congruent, which means the ratio between them must be 1 to 1. And you could use the Pythagorean theorem to then show that this side must be the square root of 2. And we can use this triangle to fill out this entire second row. The sine of 45 degrees is opposite over adjacent. The cosine is, opposite over hypotenuse. The cosine is adjacent over hypotenuse. And the tangent is opposite over adjacent. And so using that, we can fill this out, right? So that would make this 1 over root 2. That would make this 1 over root 2. And tan 45 would be 1. OK. Now we could also fill out the rest of the table. And there's 2 rows left, but we only need one triangle to do it. And we'll see why in a second. if I draw a 60-degree angle in a right triangle, then this is another case of a special triangle from geometry, the 30, 60, 90 triangle. And you could also figure that out because we were talking about how there's 180 degrees in a triangle, right? So that means this would have to have 30 degrees. And so what were the proportions to this? Well, the reasoning in geometry is based on the fact that this is 1/2 of an equilateral triangle. Like it's the left half, you're just cutting it in half. So if the equilateral triangle has side lengths 2 and you're cutting it in half, you're cutting this side of the equilateral triangle in half, making this 1. And that would make this side, by the Pythagorean theorem, the square root of 3. And this will allow you to fill out the rest of the table. So let's go ahead and do that. So sine of 30 degrees is, again, so we're starting, that's our reference angle, and it's opposite of that, which would be 1. And so it would be 1/2. Cosine would be root 3 over 2. Tan would be 1 over root 3. And 60 degrees, now we use this angle as the reference angle. So sine would be root 3 over 2. Cosine would be 1/2. And tan would be just root 3 over 1, which is just root 3. Now, something that's super interesting to notice here, and it's not just a coincidence, is that the sine of 30 degrees is equal to the cosine of 60 degrees. Similarly, the cosine of 30 degrees is also equal to the sine of 60 degrees. And the reason for that is because if we go back to our triangle, sine of 30, so opposite of 30 is 1. But if you think about it, that same 1 was the adjacent side when we think about the cosine of 60. So that's why they're the same. In general, when you have two angles that live inside a right triangle, the cosine of one of them will equal the sine of the other one. So the way that we can say that more generally is that if you have the sine of theta, it has to equal cosine of the other angle in the right triangle. And if everything adds up to 180, what would that be? So theta plus 90 plus something is 180. And so the theta, you'd have to cancel out theta, and you need 90 more. So that would make this 90 minus theta. Make sure you could do the algebra on that. So that's going to be a special fact that we're going to explore a lot more later. But before we do that, let's just dig in a little bit into just one of these ratios. Okay, so let's just forget cosine and tan for a second. And let's just think about a couple values of theta, which are a little bit interesting. So some very small values of theta and some very big values of theta. So to represent a small value, maybe we could think about 1 degree. And to represent a big value, maybe we could think about 89 degrees. Okay. So before reaching for a calculator, let's try to reason through it. So 1 degree. So if that was 1 degree, how would the triangle look? It would look much less tall than it is, right? It would be much flatter. So to draw something very flat, so here's a base, and then 1 degree liftoff would be like super tiny. So this is probably more than 1 degree, but it's hard to be exact with this, obviously. So let's say that is around 1 degree, which would make this 89 degrees. Okay. So even though we're not going to be able to precisely figure out what sine of 1 degree and 89 degree is, let's try to get an idea, right? Let's not try to have to rely on a calculator just to have some idea of what's going on here. So the sine of 1 degree is opposite over hypotenuse. The smaller the angle gets, the smaller this opposite gets, right? And so this is going to be very close to 0 because this side is tiny compared to the hypotenuse. So sine of 1 degree is very close to 0. And sine of 89 degrees, we can use the same triangle, opposite over hypotenuse. Well, opposite now, it's much longer. It seems very close to the length of the hypotenuse, but the hypotenuse is always going to be longer because it's always the longest side in a right triangle. So the sine of 89 degrees looks like it's about 1, but it's a little bit less than 1. So we've managed to reason a few things, right? Like sine is always going to be less than 1 because it's always divided by the hypotenuse. And we're getting this feeling that as theta gets bigger, sine of theta gets bigger, starting from 0 going towards 1, or so it seems. So the point, and you should think about what happens to cosine and tan as theta goes from 0 to 90 degrees. You should think about that. So the point, though, is that ultimately, yes, you're going to need a calculator to know what sine of 1 degree is. It's around 0.017 or something like that. But you don't need a calculator to be able to think critically and get heightened familiarity over situations that seem new and complex. With that being said, do your homework, and I'll see you next class.